All right, so what we are going to do over the next few days is categorize bonds as something called intra and intermolecular forces. So bonding is one of the most theoretical concepts in chemistry. Nobody has seen a bond, okay? So we draw Lewis structures, for example, because Lewis is a scientist who developed a theory of bonding based on observations collected from scientists and the experiments they did. So what we're going to do in grade 11 is look at some new words like intra and intermolecular. And then as you continue on, when you take grade 12, then we'll talk about how intra and intermolecular influence specific types of crystalline solids. We'll talk about how molecules that have carbon as their backbone or their chain, how they interact with each other. We'll talk about later on in Unit 4 how why water creates surface tension. So if you've ever seen or ever done an experiment where you take just a simple balloon, you can blow it up with the air from your mouth and you rub it on your hair, and then you can bend a stream of water. And the reason that works and the water molecules don't all flick onto the balloon is because of the presence of intermolecular forces. If you are a biologist, you might have talked about the DNA, that it has two strands connected by hydrogen bonding. So there is all kinds of examples of why or where bonding is important. So in grade 11, we are going to build a bit on what you did in grade 10, and we are going to try to make it more useful. So in grade 10, like I said, sometimes teachers just say, this is what it is. Memorize that ionic is a metal and a non-metal. We'll talk a little bit about why and what that means. So the next lab we're going to do is properties of very common type of compounds, ionic and covalent or molecular, and we'll test those properties, and you can easily do that. Conductivity is easy to test. We'll test solubility or dissolving in different solvents, and we'll even use simple microscopes, and you'll be able to look at a crystal of an ionic compound, and they're not really crystals, molecules of covalent. And even with our simple microscopes, not even on the highest objective, you'll be able to see their structure. Okay? So, and then as we think about the more tricky bonds, it does become even more theoretical or more difficult for me to show you. So, that's more in grade 12, and then if you continue on in university. Okay? So when you have a chemical bond, that means that atoms or ions, particles, sometimes are bonded together. And sometimes it has to do with switching partners and like displaces like, or cations and anions, and sometimes it doesn't. Okay? So these two broad categories, intramolecular and intermolecular, differ by very little in their spelling, which is a little bit frustrating. The way I like to remember this, that intra has an A because they are between atoms. Inter does not have an A, so it's the other one, between molecules. Actually, if you want, you can even make this a different color. So when you have bonds between atoms, that forms the compounds that are pure substances. So these are very strong. And we'll talk about different classes of intramolecular, and some of them are so strong that you need to melt metals to hundreds of degrees Celsius, which we obviously can't do in this lab. And actually, to be honest, unless you have a very specific job, like you're a metallurgist or you work with welding or something that has very, very strict safety conditions, you work at DeFasco with steel or something like that, then you probably maybe will never make a metallic bond. So we're going to focus on the ones that are more common, like I said. When you have an intramolecular force or bond between atoms, very strong, they are broken and formed in chemical changes. For intermolecular, I don't want to write weak because that sort of implies they're not important, but intermolecular forces are vital for us to be as complicated as we are. They are vital for life on Earth. So I'm going to put not as strong. And their strength, their decreasing strength, means that you are not going to have chemical changes manipulate intermolecular forces. They will be manipulated by physical changes. So when you melt ice, melting is a chemical change or a physical change, then you are breaking the hydrogen bonds. Okay, so not the bonds between hydrogen and oxygen and water.
Sorry for the interruption. This is last call for any students that were born in 2007 or 2008 and received a letter from the health unit for immunization. Please go to the Divine Mercy Room now. Last call. Please go to the Divine Mercy Room now.
They are found between the strands of your DNA, hydrogen bonds. They are, right now it's cold. Water molecules make hydrogen bonds, and it creates spaces, bigger spaces between the water molecules, so the ice floats instead of sinks. So you can imagine if every winter heavy ice sunk and crushed all the aquatic life, right? Things on Earth would be very different. Okay, so we are going to do 6. I wrote major. Again, when you take grade 12 chemistry, we're going to expand on the definitions of these a little bit more. If you choose to take biology, you will talk about linkages instead of, she doesn't usually, or Mr. Adams doesn't usually call them bonds. So these can be, you'll see why they can be manipulated a little bit. So it's up to you. These 3 are intramolecular. If you want to draw a box once we're done describing them, if you want to do like a curly Q, whatever works for you. We're going to talk about each of these in more detail. I just want to write the basic definition for the 6 before we start. So when you have an ionic compound or an ionic bond, This is something you should have talked about in grade 10. So this is transferring electrons. Some scientists will say metal and a nonmetal. Some prefer the more broad definition cation and anion, because then when you're in grade 10, then usually your teacher will do ionic, molecular, and polyatomic, right? But polyatomic is essentially similar to an ionic bond, plus, minus, transfer electrons. So we don't need to make that distinction. They wanted that you probably did weeks and so many worksheets of practicing naming. So that's what they wanted you to do. We're gonna do something a little bit different. So it's up to you. You can write metal and non-metal. As we continue on, you might find you prefer cation and anion. So when you have a covalent bond, the covalent bonding comes from sharing electrons. And sharing electrons, maybe you have a sibling or a close family friend who you've grown up with. Sharing maybe always isn't perfectly equal. Maybe you have maybe you get two cookies, say from Tim Hortons, and your caregiver says, give your sibling one of the cookies. My daughter does this. She looks at the cookies and says, okay, to her brother, you have this little cookie. I'm going to have the big cookie. And elements do the same thing. So sharing electrons allows for flexibility. So again, when we teach you in grade 10, covalent bonding in molecular compounds, we say the prefixes, mono, di, tri, tetra, penta, those ones, then you can actually have elements share electrons beyond the octet rule. And so some grade 10 teachers, because it's the first time you've done that, it's almost like they teach covalent or molecular as the crisscross rule. You really shouldn't do that. And so again, we're going to look at covalent compounds that are going to more or less follow Lewis's rules, the octet rule, and then in grade 12, we'll do advanced Lewis structures and expanded octets. So if you think about, even if you looked at the periodic table and the basic cut we did, these were the only non-metals, right? And then all of these metals. How is it possible that life on Earth has so many compounds if these were the only ones that could share and they were going to follow all the rules? It's not likely. Okay, so when you have covalent compounds, when you have sharing electrons, lots of strange things can happen. So we say, for covalent, it's going to be non-metal atoms. Sometimes the same type of atom, sometimes a different type of atom. We're going to talk about, can there be single bonds? We're going to do double bonds, triple bonds. But none of that happens with ionic. Ionic is too boring. Plus, minus, opposites attract, repeating pattern, plus, minus, plus, minus, plus, minus. Okay, and then metallic, you should not have talked about in grade 10. Metallic bonds are a very, very special class of intramolecular forces. So one of the things as you become chemists, we would like to do is stop skipping things on the periodic table. We want to use this to its full capacity. So in the past, when you count the columns, ionic charge, all that stuff, you skipped the transition metals. You saw yesterday the transition metals are unpredictable in their reactivity, and the reason for their unpredictability is their strange electronic structure. So when you have a metallic bond, it actually forms between transition metal atoms. And the transition metal atoms almost behave like they are sharing electrons. Some people will use the term electron sea, sort of implying, you know, if you think about the sea, how vast it is, the vast area of electrons around transition metal nuclei. You can talk about, some people will call it delocalized. So local is kind of a buzzword right now. Local means close. And so if an electron is localized, that means it's close to one atom's nuclei. If it's delocalized, it can be all over the place. The picture I chose, the electrons look like what we call oscillating. And oscillating is sometimes drawn with a squiggly arrow, so you can see that there on your sheet. And the reason I chose that particular picture is...
Sorry for the interruption. If you were born in 2007 or 2008 and received a letter from the Health Unit for immunization, please go to the Divine Mercy Room now. This is last call for anybody that didn't go this morning. Please go to the Divine Mercy Room now. Thank you.
And so when you have something oscillating, that means moving. Once you have moving electrons, all kind of cool things happen. Conducts electricity as a solid, conducts heat, all that stuff. So we will scratch the surface of metallic bonds and not skipping transition metals any longer this year. And then in grade 12, we will talk about it in more detail. Intermolecular bonds, and really in grade 11 biology, you talk a little bit about DNA. You might have talked about intermolecular forces. When you take grade 12 biology, this course, sometimes in the course calendar, like grade 11 chem, they write it as a recommended course. And this, when we talk about these Friday or Monday, that's the day. That one lesson about London dispersion, dipole, and hydrogen bonding is really what you need for grade 12 bio. So don't throw out that note if you're going to take biology, okay? So once we have sharing and flexibility and unequal sharing, equal sharing, some elements are not greedy for electrons. They're okay, they're good sharers. Then you have different types of forces. So it was easy for early scientists to recognize things like rubbing a balloon on your head and bending a stream of water. Sometimes you learn that as static electricity, which is okay. When you're doing charge, that works. However, the real reason that the water stays together is because of hydrogen bonding. It's chemistry. Then they did experiments and with different fuels. That's the best one. So when you pump gasoline into your car, we call it gasoline in North America. Europe calls it petrol. And that's actually a better term, because is gasoline that you pump into your car gas? No. It is changed inside an internal combustion engine. It is changed into a gas inside. because you can imagine how reactive gases are. If you drove around and there was friction all the time and the gas was a gas and it exploded, think about the gas that comes out of our gas taps, how easy that is to ignite. Imagine if that could happen inside your car. You would be driving and people's gas tanks would be exploding all over the place. So they changed the conditions of the reaction. Gasoline, liquid, is way, 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 way less reactive. And so then inside, there are pistons inside an internal engine. They warm it up. A car gets hot and changes it into a gas. The gas can then mix with oxygen. Bob's your uncle. Combustion happens. The spark plug makes a spark. The car goes. Okay. When you have natural gas, which comes out of our Bunsen burner taps, that is called, its chemical name is methane, which is one carbon. Does anybody know, anybody ever heard, gasoline is not a pure substance, but the compound in gasoline, sometimes they call it even the rating, like octane rating. How many carbons do you think are in octane? 8, yes. And so 8 carbons means you can literally think of it like an octopus has 8 tentacles. You can imagine if you encountered an octopus, those tentacles could wrap you up and hold you close. So the more atoms, specifically carbon in this case, then those molecules are held closer together, creating a liquid. So in the past, they didn't use octane. They used kerosene in their lamps, which burns really, they call it, it's called dirty, which means that it's really hard to control the incomplete combustion products. So you can imagine things like carbon monoxide could easily kill people, when using those lamps. So obviously, as we've gotten more technologically advanced, we picked better fuels, but the idea is still the same. Kerosene lamps have liquid in them. And so once they discovered that it was carbon, it didn't make sense. Well, if they're both carbon atoms in the molecule, why is one a liquid and one a gas at room temperature? So London dispersion forces, they are the weakest intermolecular force. Every compound has them, but the compounds that we're going to call nonpolar or equal sharing of electrons, that's the only force they have, okay? So they are a little bit weaker. Okay, if you don't know what nonpolar means, that's okay. Again, so a little bit of a chemistry foreshadowing. By the time we're done this booklet, you're going to be sick of the words nonpolar and polar. We're going to talk about them over and over and over again. So I'm just going to skip to hydrogen for a second because maybe if you took 11U Bio, you talked about these. So hydrogen bonding is the strongest intermolecular force. And so the good news is a little bit of the clue is in the name. You need a hydrogen atom. And then 3 very, 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 very electronegative elements. So nitrogen, oxygen, and fluorine. They're They're the top to the right. So when we talk about these more, some people remember it like FON or NOF. You do you. But we'll talk about that again, okay? And then dipole is basically what's left over. I feel like this is not good English, but I'm going to call it they're in the middle. So the middle strength. So if you took biology and your biology teacher kind of maybe spoke about polar, nonpolar, made you memorize it maybe, we're going to, again, start to switch to quantitative and not qualitative. So we're going to use the electronegativity values to help us, the number, to help us determine what kind of bond there is. Yeah. This means no poles. So what has poles? Pardon? Oh, yes. Okay. Like ends, different ends. The Earth, North Pole, South Pole, and they're different. So if there's poles, there's going to be a difference in the molecule. If there's no poles, it's equal. So that's basically what it is. Yes. Yes. Okay, so here's where I changed something. Yes, and I hope that you don't get mad at me, okay? So we are going to talk about ionic and covalent for like a week and a half. That's going to be our lab. We're going to draw Lewis structures. We're going to do all kinds of things. Metallic, because it's transition metals, is weird. And I can't melt metal atoms in this lab. So we're going to do, I think there's 2 slides about metallic atoms, and that's it. Okay, so what I wanted to do was get them out of the way. When we talk about strength, ionic versus covalent versus metallic, it's difficult in grade 11 to decide which is stronger and which is weaker. You don't have to worry about that. That would be like you have become a metallurgist and you're going to look at that. That would be like career doing, okay? Even past university. So these, we're just going to say that intra are stronger than inter, but then when you do the inter and we do that note, we're going to talk about this being weak, middle strength, strongest. Okay, so you don't have to worry about which of these is stronger. Just know they are strong, all of them. Okay, so the order of those doesn't matter as much. So we're going to do metallic bonding first because we're going to do the least with them. That doesn't make them not important. They're just tricky, as always, with transition metals. Okay, so this booklet is going to focus on intramolecular. And then the next one will focus on inter. Okay, so metallic bonds, a lattice. What is a lattice? If you have a porch and you might have, some people will call it lattice work, where it's like a crisscross pattern under your porch. Really what it means is in chemistry, there is positiveness and there is negativeness, and it creates kind of a pattern. Some are very rigid and brittle, and they will shatter. So the pattern is really strong, and some of them aren't. Okay, so just to remind us one more time, what type of metal atoms have a unique, unpredictable electron arrangement? Transition, yes. Okay, and so the reason I posted this note so late was because I was trying to find a good flat 2D picture to help us think about what this means, and it's difficult to do. Okay, so we stop at 20 because for Bohr Rutherford, the next element is 21, which is a transition metal. It would be very incorrect to draw a Bohr Rutherford diagram for scandium, okay, etc. You saw yesterday that zinc produced hydrogen gas and acid, copper didn't. What's going on? And the reason is this strange electronic unpredictable structure. So when you have the core, we usually use circles to represent nuclei. Are they really circles? No, but it's okay. So this is going to be a nuclei or nucleus. A nucleus and inner electrons. So it's going to be positive. And the reason it's positive is because there are more protons than electrons. So then instead of the valence electrons traveling in the orbits, 2 in the first, 8 in the second, they are free to move around. So even though this picture seems strange, the reason they've used this squiggly arrow, and that's one of the reasons I picked this particular picture, is because it's trying to emphasize the electrons are moving around. They are not stuck in Bohr's orbits. No way, okay? So should you continue in your science journey, you're going to talk about how photosynthesis works and that the light, the electrons, it excites the electrons in chloroplasts and photosystems, and they get excited. And the way that your biology teacher is going to draw these excited electrons is using this because they are oscillating and moving around. And once you have moving around electrons, all kinds of cool things can happen. It can provide a path for electricity to travel. It can provide a path for heat and thermal energy, and nothing is stuck. So you can melt these metals down and create brass and bronze, which make a transition metal tougher. So, as human beings, you might have brass doorknobs. Maybe your parents loved your little baby shoe and they put it in bronze to keep it forever. Maybe you have trophies that you want to keep forever. But transition metals themselves, as you know, really do tarnish. Metals do tarnish. So putting them with another metal, like an alloy, can make them stronger. So metallic bonds we use them commonly. It's not common for you to make them. Again, that would be a very, very specific type of job. Still cool, but very specific. Okay? So this is my best picture on a flat piece of paper to show what's going on. So metallic bonds form between atoms with similar electronegativity. And I didn't put transition metals on here specifically. That's what we'll focus on. So if you want to write like transition, you can. We wrote it in capital letters on the other slide. It's up to you. Okay? I felt like there was enough words on this slide already. So the valence electrons are loosely held, which means they move freely. That's the same thing. The fancy term for that is delocalized, or no particular place. And that is why we skip them. You can't count the ionic charge with the columns. You can't draw Bohr-Rutherford diagrams. They do not exist in that configuration. The electrons are not confined. They are not localized to one atom. So we're going to talk a lot about sharing and transferring, and it's almost like the electrons are being shared. So another reason I like that picture, it does have the plus. So there is the metal nuclei is positive. The electrons are negative, so there is still some plus minus attraction, but it is not rigid and it's called directional. It's not plus minus like ionic. Okay. So what does that mean? It enables these metals to conduct heat and electricity. Because of the mobility, it provides a path. So in Canada, we use copper wiring. It can be drawn ductile. It can be drawn into a wire, hammered into a sheet, or malleable. You might have copper pots in your home, and you would know if they don't have rubber on the handle, you have to be careful because the heat transfers in the copper. Some people like how it cooks, whatever. Okay. Oh, the second thing people always ask me, are we going to have to draw this picture? And the answer is no. Okay. We are going to draw Lewis structures for ionic and covalent. We are not going to draw Lewis structures for metallic. Okay. Okay, so when you have an ionic bond, there is going to be, yes, force of attraction between a positive ion, really simply, like you would have said in grade 10, metal and a non-metal. So when you have an ion, ionic compounds are going to follow the rules. Yes. So sodium has 11 protons and 12 neutrons. If it loses an electron, then it's sodium plus 1. So when you do ionic compounds, when we draw the Lewis structures and when we write their names, it will follow the rules. You can count the columns, do the crisscross rule. They are crystal shapes because of this rigidity in the pattern. Plus, minus, plus, minus, plus, minus. Okay? The thing with ionic that is importantly different from covalent is the transferring of electrons. The metal loses or gives the electrons up, and the non-metal does not give them back. So when we draw Lewis structures, that's going to influence how we draw the structure compared to covalent. We're going to calculate the difference in their electronegativity values. It is large. So metals have a low electronegativity. So the convention is that we say sodium chloride and not chlorine sodiumide. We write the low electronegativity first. So this is what we're going to do in Unit 2. We're going to write the lithium fluoride part. For now, all we've done is this. Lithium is in column number 1. It's going to give up 1 electron to form the lithium ion, which is isoelectronic with helium. Fluorine takes that 1 electron to form the fluoride ion, which is isoelectronic with neon. So when you have ionic, they are going to follow Lewis's rules. Octet rule, stable, want to become like a noble gas. The attraction is there, the opposites attract, of course. And what that creates is a crystal. So when you do the lab next week, you're going to look at the microscope and see the crystals. And like I said, it's easy to see. You do not have to have that high of a objective. Sometimes we just call them salts, table salt, road salt, de-icing salt. That's common. Your textbook is the only place that does this. We're going to need this vernacular in Unit 3. I put it in here because it's sort of weird, but they call ionic compounds formula units, the textbook. We'll usually just call them salts or ionic compounds. Technically, the word molecule does not apply to ionic. It's only for covalent. We'll talk about that tomorrow. They are very hard and brittle because of the plus-minus directionality in their bonds. They have high melting points. They do not form molecules. And what this means, the transferring electrons not giving the electrons back, is called dissociation. So ions are created. Not ions are created. The ions are present when a ionic compound dissolves in water. This creates what we call an aqueous solution. Okay, so if you saw this when you looked up the reaction, that means dissolved in water. And again, we're going to consider the conditions of reactions. Almost never do you do labs with solid ionic compounds. They're useless. They're not going to displace. You need aqueous solutions. Okay, so why do aqueous solutions conduct but solid ionic compounds don't? Thank you. Because in order for conductivity, just like in a metallic bond, you need free electrons or free charge. So when you have an ion that becomes broken apart, then the ion is free. And now you have a charged path for the electricity. If you have pure distilled water, there shouldn't be any ions. Why do we use distilled water in experiments? Our tap water is full of them. And some of them we add. Some of them are because we're part of the Canadian Shield. Maybe your parents have complained about hard water. They don't mean hard. They mean full of ions. And it messes up soap and clogs up your dishwasher and stuff like that. Okay? So solid ionic compounds do not have ions. Free ions. All right. Actually, I'm going to write free cations and anions, not just ions. So when we test conductivity, you are not going to put the conductivity probe on a solid piece of table salt. It would not conduct. We need the water.